All right, so what we will talk today about is a little bit on how we solve problems and what we have learned so far. And then we can kind of test a little bit like how we got here. So the code that we write is mostly to communicate with other humans. And the same, like what we are learning here, all the concepts and all the terminologies to communicate with the team, like with the others. So there are kind of two concepts which you may or may not be familiar with. So do you know what code smell is? Yeah. Yeah, it's kind of a bad patterns, bad solutions, which kind of feel like it does the job, but it feels like it's wrong. Like there is something kind of not right with the code, right? So let me just quickly go to code smell on Wikipedia. And they have some examples. There are some like master projects and bachelor projects about like detecting code smell in the code bases and then like highlighting it and so on. But they are kind of typical ones. So duplicated code is like on the top of the like avoid this, right? If you have to copy and paste code in multiple places, that means you're doing something wrong, right? And another one is called shotgun surgery. So if you need to change something, like the requirements changed, and then suddenly this change has to happen all over the place, right? That means you also have done something wrong, right? That means the code kind of smells because you should, if you have to make a change, the change should be located in one place, right? Very often this is because you've used magic number. Where are magic numbers? Yeah, here. So like if you have some constants all over the place and the constants change, suddenly you have to change it all over the place. So that the magic numbers or magic constants can lead to shotgun surgery, right? And then another one, which is like the God object, like you building some object-oriented framework or system, and suddenly like one class kind of grows and grows and grows because you kind of need to coordinate a lot of things, right? And you have this God class which controls everything, right? So you can kind of read about it a little bit more and try to avoid those kind of bad patterns, bad kind of anti-patterns. What is dry? Dry stands for do not repeat yourself. So it basically it's the kind of the same mantra about code repetition, right? But it may be something not literally copy and paste. You might have like a function which is doing some things, and you may have like a two loops or two if statements, and then you have another function which has to do almost exactly the same thing, but there are some that like small changes, and most of the things is repeated again, right? So you're repeating your loops or you're repeating your if statements, and it's like you like again it is like a code smell, and you should think how can you do it once in one place, varying like what is different, right? So if two pieces of code are too similar, that means you're doing something wrong, because it should be one piece of code which is kind of doing things in two different ways, right? And then you always have to think about like how easy is to read the code, how easy is to maintain it, like if I need to change it or if I need to update my dependencies, like what impact my code will have, and how easy is to add new features, right? So if you need to add new things, how easy it is, right? A lot of people, when they start their career, really pay attention to this. And then what it leads to is over-engineering. You kind of say, yeah, if I need this, I have all this framework here, and it's so flexible and so great, and I can do this, and I can do this, and I can do this, right? So extensibility is fantastic, right? But then it's like, why? Why would you have this fantastic extensibility if that is not in the requirements, right? So we have to balance it. Like, so those two, you always try to maximize, right? But this one, you try to find a balance. Like you don't want your framework to be too robust, too kind of flexible, because then it's too complex. Like you over engineering it, right? If it's like too rigid, and you cannot extend it anyway, that's bad as well. So you have to find a balance. So this one is about balance. These two, readability and maintainability, you always need to maximize, right? All right, so far so good. So another really big point is we have to talk to the product owners. We have to talk like, what should we do, right? What is the goal of what we're writing, right? It's not what we have in our head, but what the product owner has in their head, and then you have to do it, right? So let's do a very simple example. So that's the requirement. The product owner, me, says, you have to calculate the sum of numbers, and the user will give you the numbers as string, right? Do you know what to do? All right. So can you implement it? All right. Good. We have some people who need more information. All right. So what do you need more? What do you need to ask the product owner? Yeah. Exactly. Very good point, right? What are the numbers? Are they floats or are they integers? Are they in binary? Are they in hex? Like what are the numbers? What is the biggest number, right? Should I use like U64 or U128? Or is it like small numbers, like the U8 will be fine, right? So I need to know about my type, so I need to know like what is the range of the numbers. Are we dealing with negative numbers or only positive numbers, right? What should I do? Is it like comma separated values or like space separated? There is a lot of questions, right? So like it seems like this is an obvious task. You already know what to do, but you don't. You have no idea. You're making a lot of assumptions in your head, right? You're thinking, yeah, they must be integers. They must be separated by space because then I'm gonna use words to kind of tokenize it. Like, don't make assumptions. All those assumptions are wrong. You have to get the specification from the product owner, right? Don't make assumptions like in places where you don't know. Ask, right? So that is like a very trivial case where we all jump in and code the solution, and then it turns out, yeah, the numbers were actually in hex, right? And the whole thing like doesn't work, right? Because we make assumptions about integers. So you kind of need to ask the product owner to what it is that we are actually doing, right? Easy? Easy to understand, really hard in real life. We all make assumptions all the time, right? And then it turns out there is a lot of bugs because we made wrong assumptions, right? Yeah. When Microsoft came up with their first operating system, they made an assumption that no computer will have more than 480 kilobytes of memory. That was the assumption, big assumption in the operating system, right? It very quickly turned out to be wrong. And then we had a big mess because like we had computers which were more than 480 kilobytes of memory. And then what? DOS was not really working that well, right? Okay, so let's do a little bit of a check, a test. So, and then we'll have a break, right? I promised to have a break in 3 minutes. So we have a function, and the function takes a string and produces a list of ints, right? So if I pass it like 48, 33, and 12, space separated, I'm gonna get a list of those three numbers. Actually, obviously that is wrong. Let me quickly fix it. So it's 12, 33, and 48. Yeah, that's what we want, right? So then the question is, we will use that function. So remember, this function is called string toList, str toList. It takes a string and gives us this list of integers, right? And now you have to write a function which is called add numbers, which takes a string of those numbers and gives us the sum, right? So we're gonna use this function to write this function, which takes a string and produces an int. So how can you do this? So join in. Jesus, 41 questions. We will be here for the whole week. Who created this lecture? All right, come on, join in. Join in. So we have string to list, and now we have this add numbers, and we need to write this function, assuming this function exists and we already implemented it. All right, so let's try it. Trivial, one might say. Just the definition. No, the type, you don't have to specify the type, just the one-liner, which is add numbers and what it equals to, like whether you there are multiple ways of doing it, obviously. You basically have to combine two functions, right? You have to combine the sum and the string to list, right? Yeah, this one is correct. This one is not correct. This one is correct. So there are some correct ones, which are kind of not like it's a robot because I said add numbers equals. So like the full definition, not only the definition part, but this is like the idiomatic way of solving it. So whoever said that, it's kind of correct. Yeah, let me check if I can give points for this. No, I don't know how to do it. Yeah, anyway. The idiomatic way is to do this. And this one, like we could put str as an argument and then add the argument kind of at the end, right? But we normally in Haskell, we don't do that, right? So if I go, come on. Let me see. Yeah, so then we have add numbers, and then we can say that our string is here, and then we say sum string to list, and then we have to pass that string argument here, right? You can say, yeah, I need to do this first. So I need to convert my string to list. Then I will have the list. So then I do the sum on the list. That would also work. But that is like, why is one solution kind of more idiomatic than the other one? Because of the way we think and about the way you kind of express what the code is doing, right? It's a very trivial one-liner, but here you kind of communicating, yeah, do this first, and then do this. Like you kind of thinking in a very kind of a structured and very non-functional programming way, which comes from like Golang or C or C++, right? And if you say, yeah, actually what I am doing is I have a function which combines two functions in my solution, and then it takes an argument, then you end up with the combination of two functions, and then you say, yeah, my solution is composed of two functions. And then that's the solution. And then it takes an argument, right? And then it takes this string argument. But because of point-free notation, we can delete all of this. And then we say, yeah, the solution is the combination of those two functions. You cannot get any simpler than this, right? So you say, yeah, I'm combining those two functions to get my solution, right? All right, so let's have a break. I will. All right, so I figured out how to give the points for people who did it correctly. This one is not correct. So the point-free notation, like it defines a function, and the dollar sign, it's kind of a bit like it gets a little bit used to because it's a little bit counterintuitive. Okay, we're gonna go back to the dollar sign in a moment, but like this one basically creates a new function which takes one argument. So this is a function which takes one argument. This one argument goes to this function. It does what it needs to do. And then the result of this is passed to this function. This function does what it needs to do. And that's the result of like processing, right? With the dollar sign, like if I replace it with the dollar sign, it's a little bit different because the dollar sign is not a syntax. It's a function in itself, right? If I go to GHCI and I ask it, okay, tell me about the dollar sign, it will tell you, yeah, the dollar sign is a function which takes two arguments, and the first argument is the function, and it kind of passes what the second argument is to the first one to get the B, right? So, and it's in infix notation, right? So if I have +2 and I have a dollar sign in infix, and then I have 2, so the dollar sign is a function which on the left-hand side has a function, and on the right-hand side has a value which that function needs to compute the output. So this is not like, this does not take any arguments, right? It is a function which takes the first argument and gives it the second argument and computes something, right? So kind of qualitatively, this is really different to this. This one expects a function on left and right hand side, but this one expects a function on the left hand side and a value on the right hand side. This value needs to be given to that function, right? So it's so I said, yeah, this is correct, but it is not correct. Like you actually you had a good idea, whoever was doing this and this, but it has to be a dot. It cannot be a dollar sign, right? So then there was a question about typos. Like, is it a typo or is it like a wrong code? It is a wrong code, right? It's not a typo. Like it's like the thinking is correct, but the syntax is wrong. So again, here it's fine, but we discussed this. Like this code is fine, but this code in Haskell smells. And why it smells in Haskell? Because you're kind of doing kind of imperative, trying to do imperative programming. You're trying to tell somebody, look, I'm doing this, and then I'm doing this. But it's like, no, you're not doing that. What you're doing is you're combining those two functions, and then you're applying the combination on the argument, right? So that's why this one is correct. It will work, but it's a code smell, like in Haskell, right? The mental model is wrong because the mental model communicates that we doing this and then we doing that, right? It's the same here. It's the same problem. We saying do this first and then do the sum, right? You're telling the reader like what to do in which order. That's imperative programming. It's not declarative, right? Declarative is saying I have a function which takes an argument and does what needs to be done, right? So this is the kind of the idiomatic and clean way of doing it. You can say, ah, come on, it's like does not that it doesn't matter, right? This code works. This code works fine. Why should we care, right? Yeah, the thing in programming is that a very small little smell, if you have 10,000 lines of code, compounds to something that is like super hard to maintain or super hard to work with, right? In this one liner, there is no difference. I mean, if you do it this way or if you do it this way, no problem. Like it will work, it's fine. I can read what you're saying and it's no problem, right? But if I have 10,000 lines of code and each of the lines is doing something a little bit off, at the end, I'm getting a code base, which is like really, really difficult to work with, right? So those tiny like OCD kind of things are important. You kind of need to have a little bit of OCD to kind of pay attention to those little things and fix them, right? And that's what we do by code refactoring, right? Usually we type our code, we compile it, we make the compiler happy, and like it takes some time, especially in Haskell and Rust. And then once we do that, it's like, yay, it works, right? And then you kind of stare at it and say, yeah, but kind of I feel it smells a little bit. And then you kind of try to beautify it. You try to refactor it such that it kind of like is easier to maintain and kind of nicer. So then this, what you would start with, and then you would convert this to this. You would actually make it better, right? All right. So we have now our solution to add numbers, no problem. And most of you, like honestly, most of you got it right, even though it was not necessarily idiomatic way, right? So great. So now we need to implement this string to list function. So we have map, read, and words. And now we have to write this one-liner for the string to list. Again, I'm using 30 seconds. That's not enough. Mariusz. Okay, let me fix it. Let me give you more time. Mm, 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 mm. All right, will it work or will it reset? No, it probably will work. All right. Obviously, don't cheat like with the Copilot. Try to do it from head. All right, so those two are correct, although obviously this one is not idiomatic. This one is the idiomatic way of doing it. It's a little bit more complicated. So the counterintuitive thing is in Haskell, the space and the dot, they have meaning. They are kind of like a keywords in the language. The space especially is like a keyword, right? So the space is a function application. So by making space, we're saying apply function to the arguments, right? It's kind of the same as brackets in like Golang or normal languages. You say function and then you say brackets. That means call this function, right? So space functions as brackets in the imperative programming languages, right? So here we have this space, and it means apply read to map as an argument, right? And space has the highest precedence. It's like it's the most, like, you know, when you have plus and multiplication and so on, and you write them together, like the multiplication is higher precedence than the plus, right? So space has the highest precedence. So the space is bound first, right? So that means here we have a carry. We have a carry of giving, like, how many arguments map takes. What do you need to pass to map? 2, right? You have to pass the function and some container, right? So map takes 2 things. So if we have map with 1 thing, we have a carry, right? And the carry waits for 1 more argument, right? So that means that can be our 1 function, which is 1 argument function. And then what words does? Words splits the list of strings into individual tokens, right? So like if I have yeah, like if I do words on mama tata, then I will have 2 things, mama tata, right? All right, so that is also a function which takes 1 argument, right? So when we combine them together, now the whole thing is a single function which awaits for 1 argument, and then this 1 argument is our string. The words will split it into the list, and then the map will map read into that, right? So this is exactly what this code is doing as well. It says, okay, I have to do words on X first, but then I need to do map read on the result of what this is doing, right? And this is a typo because, so let's try it out. Let's try it out why it is a typo. So I will show you. So this code will not compile because that thing here is wrong, right? But we want to get this. So if I have string to list, and if I say X, now I say read words X. Okay, so then if I try that, it will blow up. So that's an error. If I delete this, it will almost work, and it will blow up as well. Yeah, actually it didn't blow up. Let me try. Yeah, so it blew up now, okay? Why? Why this blows up? Who knows? Yep.
Something how read works.
Yep, something to do with read. It kind of says here, we have an exception, read didn't work, right? The error message is a little bit like, read didn't work. Yeah.
Does it need a type?
That's right. So read is a polymorphic function, and it converts, like if we ask, okay, tell me about read. It says, well, it's a polymorphic function which takes a generic type, but this type has to have this meta class, right? It has to be readable. If that type is readable, a read can convert a string to that type, but it doesn't say which one, right? Which ones are readable types. So we can ask, okay, tell me about read. And then it tells you all about read. And it, for example, tells you that read has a lot of instances. And one of those instances is integers. Integers are readable, right? If I have a number, I can read it from a string into a number, right? But our implementation does not know that what we are reading are integers, right? So we have to tell it. We have to tell it that actually the result will be a list of ints. If we do that, then it will work, right? Because it will know, oh yeah, now I know what to use, what polymorphic version of read to use. I have to use the read, which reads strings into ints, right? So that's what you can also ask. You can say, okay, tell me about read, which is the one which takes string into an int, okay? And I didn't really like that one. So let me see if this will work. Yeah, anyway, like I am kind of coercing that particular polymorphic read into string into int, right? Because the generic one is string into a, and a is like a generic type. So this symbol is like in Rust we call S. In C we do casting, so we casting it to a particular type, right? Haskell is a strictly typed language, and we can cast things to a particular type, and then this symbol is like for casting. So coming back to here, if we cast it to an array of ints, that this result has to lead to the list of ints, then it will work fine. But we don't have to do the casting here. We can do the casting like when we call it. All right, so we have some people doing second time better than the first time, and one person did both correctly. Perfect. So now this is the idiomatic way of doing the string to list. So we mapping read on what is done here, and then again we using point-free notation. We're not passing an argument here, and we're not passing an argument here. If we were to pass an argument here, we would have to use $, right? We would have to say, take that function on the left and apply it to the argument on the right. All right. So having learned all of this, we have this code. It's generated by LLM. We ask it, write us this decode message function, because we have a lab where we have to decode those alien messages. And it kind of did this. And then we stare at it and we see what? We see that it didn't do the idiomatic Haskell way, right? Why? So how could we fix it? Will this code work? Will this code compile? Yep. There is nothing wrong with this code. It will work. It will solve the thing that we need to solve, but it smells. So it smells here in this line, and it smells here. If you see lines where there is a lot of $signs, that usually kind of suggests that there is something wrong. Can we avoid $sign here? Also, when you see lines where you have a lot of brackets, that usually also indicates, yeah, you're probably doing something wrong. So can we avoid the $sign here? Not really, because we want to get the numbers. And the parameter is here, and we cannot really use a point-free notation. So we have to pass the parameter. So we probably have to pass, we have to use the $sign at the end, such that we say, yeah, like we're doing the left-hand side of $sign, and then the value, the argument, the message is on the right-hand side, right? So this, what we will do is we kind of move this one to be here, and then put a dot instead of the $sign, right? How about this one? Yeah, it's the same story. Like it's very imperative way of thinking. Like I have to do this filter first, and then after I've done the filter, I have to calculate the length, and after I calculated the length, I have to calculate the return, right? So again, we replace it with dots, and then move this guy all the way to the last thing, right? So after the changes, we'll have code like this, right? And this code is clean, is idiomatic. It kind of uses the $sign where I cannot avoid using it, and it uses a dot where it makes sense. And it kind of nicely reads as a composition. It says, yeah, we have a composition of filtering, length, and return as a single function, and this function takes this one argument. It's kind of like logically what is happening, right? We have like a function which takes one argument. Before, it was kind of confusing, like it was telling us what to do, not what it is, right? So this one is more kind of explaining like what to do step by step, like in imperative way. And this one is saying, yeah, no, what is our solution? Our solution is a function which takes those numbers, and the solution is composed by filtering, length, and return, right? Again, you may say, yeah, but they both work. They are kind of the same. It's like, yeah, it's like a small difference, right? It's this kind of like the way you present it to another human and the way it kind of works, right? All right, who knows what Pyramid of Doom is? Pyramid of Doom. If you worked with Node.js, you probably have seen it and you probably have done it yourself, right? So it's this kind of like a chain things of callbacks or chain things of if statements, which creates this sort of a pattern of code, which is definitely smelly, right? If your code looks like this, yeah, that's like really, it needs refactoring. You really need to work on improving the situation, okay? So how do we do this? How do we like deal with the pyramid of doom? Yeah, we have to linearize it. We have to somehow make it such that our code is more linear than kind of indented, right? So this is again decode message example from a lab. One of the students kind of wrote this, and you can see that it definitely follows the pyramid of doom pattern, right? It's like, yeah, like why are we doing this? Like nested, 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 and then we have the kind of final solution, right? It's really difficult to read. It's very difficult to reason about. You have to follow this kind of indentation and kind of see what happens when. And we can kind of see that we have this kind of unhappy path. The unhappy path is the left always. So we say, yeah, there is kind of an unhappy path. And if we manage to go all the way down, there is the happy path, right? The happy path is all the rights, but it reads like it smells, right? It is kind of wrong. So how can we do this? Well, we need to think how to linearize it in such a way that it kind of looks more like an imperative code. That we're doing this, we're doing this, we're doing this, and so on, right? In Golang, you have this problem. Like you're doing something, then you have to check for the error. If there was an error, you have to do something, and else you're kind of going on with your happy path, right? So in Golang, what we do is sort of say, we avoid the else. We say, I'm doing this, then I'm checking for the error, and if there is an error, I'm skipping, like I'm jumping out of the function. So then the next line of code is again not indented, it's like here, right? Again, I'm checking for an error, and I'm doing the third thing, right? So I'm kind of every time I'm doing something, I'm checking for the error, but I'm not indenting it kind of to have this sequence of doom. It's like we linearizing it and saying, okay, if we are on the unhappy path here, then we jump out. We go to the caller and tell the caller like we are in the unhappy path, right? And this is kind of what happens here as well. You say, if I'm in unhappy path, I stop, because that's the if is an expression, and then this left side is the outcome of this expression. We don't go any deeper, right? But in Haskell, we cannot solve it by if statements because you have to have else. In Golang, we cheating because you can have if expression or if statement. I mean, here is an expression, and Golang is a statement, and avoid the else, right? So that's another rule of thumb. Like when you're writing an if statement in imperative programs and you can avoid having else, you should try to do that, right? So sometimes we say check, and then if true, do this, and if else, we have error handling, right? Usually it's better to turn it around and say, if there is an error, do this and quit, and then don't have else at all, just continue with the logic, right? All right, so avoid pyramid of doom, structure your code well, and then you should use the do notation. Some of the labs ask you not to use do notation, and that's for two reasons, or three reasons even. The first reason is that by not using do notation, you understand what do notation actually is doing. It's a syntactic sugar, which makes your code nicer by linearizing things which otherwise would have this nested structure, right? The second reason is that when you are doing it without do and start using do, you feel like, oh my God, it's so much nicer. It's like so much easier to use do notation, okay? And then the third reason is most of the time, if you ask LLMs, they do generate you the do notation. So if you are forced to kind of do it by hand or forcing the LLM to do it for you, you learn like how it actually works. And it's very helpful for later on writing definitions of more complex functions, because we will have to use inner functions. We will have to use like lambdas. All right, so the indentation of doom is very typical for asynchronous programming and programming something with callbacks. So we have a course next semester, Kotlin. You will learn another programming language. And in Kotlin, it's like linearized. And also in modern JavaScript, they also try to linearize it. And also in Haskell, we kind of linearizing it as well. But in the traditional, like the old-fashioned async callback programming, you have this situation where you have this doom. So Kotlin is coming next semester, but let's have a look into the very small snippet of JavaScript where we have this situation. So we have to fetch something from the internet using the fetch command, but this command is asynchronous. So it will go on, do what it needs to fetch, and then it will come back, and then we have to handle when it comes back what to do, right? And we're doing it by having this callback function. So we're saying, okay, when we fetching a data, I'm passing it the callback here. And then when I'm actually doing the fetching, I'm passing in this inner function, this lambda, which has the response, which the fetch will feed once the callback happens. And then we have the situation where we have the data or an error, and we kind of handling it, right? So then when I need to use it, I have my function, which does something for the error or does something for the happy path. So I have unhappy path and happy path. So I created this function, pass it here, and I have this kind of nested structure, right? So we have like two levels of callbacks, right? It's the outer one, which is us, what to do, and there is the inner one for the fetch itself, right? Right. So the modern JavaScript linearizes it and says like, yeah, you can actually code like this, right? So then you say your function is much simpler. It doesn't take the callback, right? And it waits here for the fetch. And once the response is kind of given back, it kind of, if the response is not an error, then we do the JSON parsing. So we're doing this, then we're doing this, and then we're doing this, right? We have a linear structure. So remember, like do kind of helps us doing the linear structure as well, right? And then if we get to that point, we are done. But if one of these fails, we get this try catch block. So we get into the error situation and we're handling it, right? So again, happy path, very linear. Unhappy path, kind of we go off the rails, right? We go to a different thing. And then the code is much simpler, right? So if you compare this to this improvement, right? Is it easy to read this? Not really. Kind of a nightmare. Is it easy to read this? Yeah, very kind of clear exactly what's happening, right? All right, so let's pause for a second here because there are two things that I want to mention. One thing is, so let me open the lecture. Get Jobbik course. One is carries, okay? What is a carry? Carry is a function which usually takes more than one argument, but it has been filled in with partial arguments such that we end up with a different function which takes the rest of the arguments, right? So for example, if I go to plus, so a plus function takes two arguments, right? It takes a left and right hand side. But if I give it one argument only, what I will get, what I'm getting back if I do this. Oops. I get a function which takes one argument and makes the two argument function kind of happen with this argument already kind of inside the function, right? So carrying is a mechanism for making partial application of arguments to a function without like computing the whole thing, right? So I have explained this here. If you go to the wiki, I obviously, yeah. So in JavaScript, you can also carry functions. So you have a normal add, which takes two arguments, right? But then you can say, I have a carried add, which takes one argument, gives me a function back. The new function takes one argument, and this function gives me a third function back, which is the sum, right? You know this double arrow notation in JavaScript, in the modern JavaScript, right? So in Haskell, the carrying is kind of autonomous. It's like all the functions are carried by design, by default. All functions in Haskell are single argument functions, right? You say, yeah, are you sure, Mariusz? How about this? Like, how about if I ask for the plus? Obviously, plus takes two arguments, right? It's like, no, it takes one argument and then gives you back a function which takes one argument and gives you the final sum, right? So it's kind of like you see this A to A to A, and we, coming from imperative programming, we sort of like to think about it that it is kind of like this, that it takes two arguments and then gives us the result, right? But it is kind of really, it is more like this. it takes one argument and gives us a function which takes one argument and gives us the result, right? We don't use the brackets at all usually. We just kind of don't care. But whether you put brackets here or put brackets there for Haskell doesn't matter, because add takes one argument and then gives you another function which takes the second argument and gives you the result, right? All right, so this is kind of explained here. But there is another concept, really similar to carrying, but not quite. It's kind of a little bit different. And normally, you really deal with that extra concept if you're really going deep into kind of a programming runtime systems. Normally, programmers don't really think about it. And there are a small subset of programming tasks that have to talk about it. But it's very cool. And it's called continuations. So a continuation is kind of a little bit similar to carry, but instead of waiting for the arguments to happen, you're waiting for the computation to happen. You're saying, I have some computation to do, and then I have to do something else. So we kind of saying, like, we treat those, like what needs to happen next as a continuation, and we can pass it around. So you explicitly control how things are called and in which order, because you're controlling like the continuations, right? Normally, if you write your imperative program, you say, do this, do this, do this, right? And the program will do this, do this, do this. But here you're saying, look, do this after you've done this first. You kind of are turning it upside down and you're declaring like, what is the continuation after I've done this? What's next? Like, what do I need to do next, right? So here is the, like, I'm not gonna dive a lot into this. I encourage you to read this short article with the explanations. I just want to show you that normally, if you have two functions, if you have the plus and the square, and we're doing this add square square, this is like a normal flow, and you don't control like what will happen when, because it's kind of hard coded. Like it's hard coded into the structure of this computation, right? So this computation will do this no matter what. It's like one single blob, right? But you can do this computation in a continuation passing style, and the continuation passing style takes the computation that you need to do plus what will happen after this computation is done. And the artifact is this, that if we were doing this way, we would have to say print what this thing does, like print the result, right? But if you're doing the continuation passing style, we're saying do this computation, and once you do this on the result that I got from the computation, right? So it's kind of back to front. When it is useful, it's really useful for when you want explicit control of what happens in your program. For example, in a debugger, it's very useful when you want to have an undo function such that you can kind of roll back to what the state was just before you did something and you want to do something else. So like, for example, I want to undo something, right? And then if you want this sort of a callback pattern, right? Aha, callback pattern. So then if we go back to this JavaScript thingy, and you see this is exactly continuation passing style of programming. We are passing what will happen after a certain computation happens, right? So in the callback function, like all this thing which the JavaScript is doing what's called continuation passing style programming pattern. So now you know, right? You're kind of like XP level is kind of a little bit over your typical Java programmers, because you know what kind of happens here if you read the other article about the continuation passing style, right? All right. Did you understand it or not quite? More or less, right? So you probably don't understand all the details, but you can walk through yourself with the examples which are in the wiki. But you understood that there is a reason why we sometimes do this, and for callbacks we do this, and for like ability to do undo, we do it when we want to control like the order of what happens when, right? So in the continuation passing style, you're saying, do this, and after this is done, we will do this, but this will take arguments from what this has happened, right? And then we can kind of say, yeah, now we can actually go back and say, yeah, after you do this, you don't do this, you do this instead, right? We have a more explicit control of what we are doing. All right, so now we're coming back to the function composition. Man, we're not gonna run those 41 questions today. Yes, so there is a question about lab 7. There will be no checks for lab 6, 7, 8 today. I will organize additional session next week, probably on Tuesday, and advertise it. And then people can come and have their bonus points and have their labs 6, 7, 8 done in the normal way next week. And then we will do the 6, 7, 8 in the paper form in the deadline. So we will kind of do a hybrid because like I think that's kind of fair. So I will post an announcement after the class. All right. So what is this? It's an infix function which takes 2 arguments. And will it work? It's also an expression. Of course. Fantastic. Great. So yeah, I mean, if the questions are that easy, then maybe we can do the 41. Let's see the next one. So we had 2 plus 3, and now we have plus 2, 3. What's the difference? What's the difference between these, yeah? In Haskell, no difference. In Golang, what's the difference? In C++, what's the difference? So in Haskell, they are exactly the same. There is no difference because all functions in Haskell are carried. But in C or Golang or like Rust, this one is a 2-argument function application. It's a function which takes 2 arguments, right? This one is a single argument function which takes 1 argument. So there is a difference. This one is a carried version of plus. This one is a normal 2-argument version of plus, right? So there is a difference between these two. This one is a carried, which means it's partially applied all the arguments, some arguments. This one is a normal application of 2 arguments, right? So I can delete this, right? Now I have a function with 1 argument, and this argument is missing, right? Here I cannot do that. Like if I have add and 2, 3, I cannot say like let's delete 3 and like let's deal with this, right? And C or Rust or some other languages, right? You could say, yeah, it would be nice if you say I don't care and I have a carried function, right? Maybe like you will invent a language which is like this, but currently you cannot do this, right? So if you have this, you cannot really do things with it, right? So the difference is that this is a carried version of this, but the carried version gives you the flexibility of like removing arguments and like using this and passing it around to do different arguments for it, right? This one does not allow you to do that. Like you have to bake in the arguments in the call, right? All right, so next one. Ooh, the dollar sign. Jesus. Will it work? All right, so now we said we don't like this one. We don't like the 2 + 3 too much because it's very rigid, not very flexible. We like the carried version, and we have +$2 $3. Okay. What's the difference? Yeah, you're answering fantastic. What's the difference between the one with the dollar and the one without the dollar? Yeah. Yeah, there is almost nothing. The difference is the dollar. So this is a function which takes one argument and computes 5 for us, okay? This is a function which takes 2 arguments, left-hand side and right-hand side. The left-hand side is another function, and this function takes this function, gives it the missing argument, and computes 5 for us, right? So this one is way more complicated, right? How we call functions which take other functions as arguments. We call them high-order functions, right? This is a normal function, not a high-order function. This is a normal function which takes one argument. The dollar is a higher-order function which takes a function as an argument and another argument and makes some magic and gives us 5, right? So again, on the surface, they work exactly like they give us exactly the same result, but this one is way more complicated because it uses the dollar sign to do this magic, this higher order magic. And that's why I was telling you, like, every time you can replace it with dot, you should do it because dot doesn't do this kind of, like, it just composes the functions. It doesn't do this kind of higher, like, it does higher order things as well, but it's like preferable. Yeah. All right, let's go on. So let's move, like this one is the infix notation. And now we have in the prefix notation. So now we just moved it to be a prefix. No problem. We can do it. We can move it here and it will work flawlessly like as expected. So every time you have the infix or post or prefix, you can use it in either way. If you have an infix operator, you just have to put it in brackets and put it at the beginning. If you have something that is a prefix, you can do the ticks and put it in the middle and it will work, right? So Haskell is quite flexible how we use the functions in the prefix and infix. So this will work, no problem. How about this one? Yeah, we're making some progress. 7. Oh, flip. Gee, this one is a hard one. Right. Let's wait. Flip. Like, what is flip? All right. I will show you what flip is to help you. So tell me about flip. Okay. So flip takes a function which takes 2 arguments, A and B, and computes C. So it's kind of, you can think about it, it's kind of like a plus, which takes left-hand side and right-hand side and produces the result, right? And then it takes B first and A and produces C. So it kind of, the flips takes 3 arguments. And the first one is the function, and the function is binary, so it takes 2 arguments, but the arguments are flipped. So then the flip turns them the correct order for that function to work, right? Do you get it? Yeah. All right. So let's check it if you got it. Oh, crap. So with the explanation, maybe more people would get it, right? So why is not working? Why it is a compiler error? All right, you can answer here. So flip takes a binary function. Is this a binary function? Yes, it is. Do we need the brackets? Yes, we do. Which flips argument, like flips arguments for this function. What is this function doing? This function needs a function on the left-hand side and the value on the right-hand side, right? But what flip will do, it will flip it. So this function will get, so we kind of have this. We have $3 plus 2 now, right? That will not work. Plus $2 2 works fine, but 3, that works fine. But if you turn it around, if you try to do this, it does not work because the first argument is not a function, right? That's why 3 is not a function, and that's the reason why this one is a compiler error. All right. So how are we doing? There is some chasing going on, but the Ribbit is still holding on to the first position. All right, so next one. How about this one? It's kind of like puzzles, like mental puzzles. You just have to like work it out. Don't guess, work it out. Perfect. So this one is fine because flip will flip those two things. And then this guy will have the function on the left-hand side and the value on the right-hand side, and it will work fine. I personally have really hard time reading code with flips. So every time there is a code with flips, it makes my head kind of spin a little bit, like it's kind of complicated. However, flip is very useful if you have the kind of incompatible things to do. Um, like often you have to do something and it takes two arguments. But the thing that you are kind of changing is not the second argument. So like let's say you have this situation. My thing is not writing, so I will do this here. So imagine that you have to do something like do something. And then you have the first and the second argument, right? And if the second argument is changing, then it's very easy to make a carry because you can say like, let's say I have to do something on a list. So the second argument is 1 or 3, right? So then it's very easy to do that because I can say, okay, do something is a carry. And then I'm mapping it to those values, right? So like if the first argument is baked in, then I can easily do the carry and kind of manage that, right? But what if it is not the second argument that is changing, but the first argument? So the first argument is 1 and 3, and then the second is baked in, right? Then I have a problem. And my problem is that I have to vary the second argument, right? Which is here. And I cannot really easily do a carry without having the first thing here, right? But flip comes to the rescue. So then we say, we kind of just flip it. And then suddenly I can do this. I can do this. And then I do 1 and 3. and then do my map again, right? Do you get it? So like every time you are kind of like, I wish I could carry it, but it's the like, it's not my first argument that is baked in, then you can just flip it and carry it, right? So flip comes handy, and you will read code which uses flip for that reason, and it will take a while. Like it will take like, why are we flipping it? Yeah, because we're baking in this argument here and we want a carry, right? Okay, we have to stop somewhere. So we already over time and we need another break. So, whoa, brackets, Jesus, how are we gonna read this? Yeah. So the problem is like, yeah, why it is a compiler error? Actually, I have a question. So the compilation error is with this. There is kind of an easy rule of thumb with dot. And the rule of thumb is that dot is a composition of functions, and each of those functions has to be a unary function, single argument function. You cannot compose a function which takes two arguments with a function which takes one argument, because the flow of arguments would not work, right? It does not make sense. Remember the railways? Like if we have like a railway with two things, we have to kind of bind it or do something more fancy, because the two things kind of are incompatible with the railway, which is just one argument, right? So the dot combines functions which take one argument, right? And then the right-hand most function gets the initial argument, produces something, and then the second one gets the result of this one, and so on, right? It flows like right to left. But flip, how many arguments flip takes? Flip takes 3 actually, right? Because it takes the function, the right-hand side and left-hand side. So flip takes 3 arguments. How many arguments $sign takes? 2. So like we cannot use dot, like for sure. Like we cannot use dot here because neither this one or this one are unary functions, right? Usually it's the same with plus, but we often use plus with the first argument baked in, right? So then we have a carry which just takes one argument, and then you can use it with dot, right? Right. Yeah, exactly. So $$ needs 2 arguments. We have to have unary function and so on and so forth. So the reason why it does not compile is this dot not between unary functions. All right, so here it's a kind of a good break. So I will stop. We will continue that lecture kind of next week, I guess. We kind of didn't go far. And we will have a break, and then we will do this experiment with the paper, okay, and pens. How many of you don't have a pen? 3. Yeah. So I'll bring some pens, and then let's have a break, and then we write a quiz.